That's it.
One person online.
Okay, good luck.
Right, folks.
Well, enjoy your life.
Any Manchester United fans here? Right. Oh, let's get stripped down. If you remember, 2 weeks ago, we were looking at distance classifiers. Distance is physical distance in multi-dimensional space of patterns which are vectors which become points. Good evening. Which become points in that multi-dimensional space. And in a distance classifier, you are using the principle that closeness in physical distance is closeness in perceptual distance. Because what these things have got to mirror is what we regard as similar in the real world. It's got to map real world things. And in a way, that hand is a hand, that is a different hand. If you were a young child and you only saw that as being a hand, you wouldn't recognize that. And that, of course, is, in terms of pixels, a very different pattern from that. But of course, in terms of perception, that's a hand, isn't it? So is that. You see the problem, because there's all the hands coming through. Tens, hundreds, thousands, millions, billions at the pixel level. So the Euclidean distance, let's call it dE, was the summation over I equals 1 to d, there's your dimensionality, of AI minus BI squared. Doesn't matter whether you get those round the wrong way, BI minus AI, exactly the same, because you're squaring. And of course, that calculation of distance increases with d. And the summation there, the subtraction, d operations, the summation there, d operations, but the squaring is the multiply. And the multiply is your complex arithmetical operation. Shift and add, for as many times as you've got it. That takes most of the time. Now, in 2 dimensions, absolutely trivial, but we can look, see what's going on in 2-dimensional space. What we have for the Euclidean distance is 2 dimensions. This is dimension 1, and this is dimension 2. And for a pattern, x, that would be 2, 2, say. X is the vector, 2 for dimension 1, 2 for dimension 2. That is the point of the vector. And for a Euclidean distance, the contour of equidistance is a circle. And the different contours will be consecutive circles. Pretty obvious when you were junior school, triangles, Pythagoras and all that. So that's quite obvious. And of course, if you have 2 classes, you will have 2 sets of contours. They will eventually overlap. And if you draw it accurately, you will find that there is a decision surface. There's pattern red. There is pattern red. There is point X. And the decision surface is going to be the line at right angles to those 2 reference points, passing through the midpoint, and that will be the decision surface. Now, to classify unknown patterns, an unknown pattern comes in here. Oh, come out. We would simply measure 2 distances. We would measure D1 by that calculation. We would measure D2, and we would find which is the smaller, which is the closest. And clearly, by observation, that blue cross is on the red side. So this, all the decision surface of all the patterns on this side of the decision surface will be red or will be blue, unless you apply a threshold distance, in which case you can reduce the clusters. I think that's very obvious. So The decision surface tells you how these systems work. But the good news is you don't ever have to calculate the decision surface, because you can apply that decision surface by measuring the distances and find out which is the closest. And that's good news, because in 2 dimensions, the decision surface is 1 dimension, it's a line. If I go to 3 dimensions, this room, supposing I was classifying a perfect male there from a perfect female there, just using those 2 patterns, where everybody else disappears, there would be a plane, chunk, going through there, which would put the males on that side and the females on that side, assuming that where you sit is related to your sex or gender or whatever way you want to describe yourself. And of course, that's a nonsense problem, because if I have the decision surface coming through there, yes, you're a male, you're okay, you're a male. Females on this side, yes, you're a female, you're a bit dodgy, you're a bit dodgy. And of course, then there's the philosophical question, what do we call people on the boundary? And I don't want to go there. But it's possible. So that was the Euclidean surface. T gets up to the tens, hundreds, thousands, millions, and D could be in the millions for taking pictures directly into vectors, because then the pixel value would be each element. And if I wanted to represent a picture as a vector, it would have, for standard resolution on your phones, it would be something like 4,000 by 4,000, 16 million elements, and each pixel, red, green, blue, would be 24 bits. And that turns out to be about 16 billion. So again, your big data comes in there. Wow, how many possible pictures are there? Well, it's 16 million to the power 16 million. And don't put that in your calculators, you can't even do 10 to the 40. It's a big, big number. So, next stage was to approximate the distance. And the approximate distance I gave you last week was the city block. And sometimes, if you're in America, it's called the Manhattan distance. Presumably because it looks like the street patterns in New York. And for the city block, we calculate dCB is equal to the mod of the difference of the elements, corresponding elements. And again, it doesn't matter whether that is the other way around, because you're taking the mod. That removes the problem. And of course, it's a summation over all dimensions, I equals 1 to D. And when we come to evaluate the contour of equidistance for the city block, and I hope you've done this in your own time and plotted it out accurately, because my diagrams are just sketches. Do it on Graph Breaker to see exactly what's going on. If I take a pattern there, we find that the city block contour is a diamond, or a rhombus, or a square on its side. I don't care what you call it. And that is the contour of equidistance, which means that every point, every test pattern on that red line is an equal distance from the center pixel, if you're using that metric. And of course, when we plot out this for 2 classes, there is a pattern there, and there is a pattern there. Put in my Euclidean distance, which looks something like that. That's Euclidean. Decision surface. And the city block will appear something like this. And I call it a dogleg. And that is because the contours of equidistance are not circular. And the beauty of circles is if you overlap them, they will only intersect at 2 points. Whereas a linear, piecewise linear contour will possibly overlap on the linear parts. And so what we have here is patterns on the red side on this side of the red surface, the city block, will belong to the black class, and patterns on the black side of the red surface will belong to the red class. So we have an area of ambiguity, and I can shade that in. It's out here, and as we get further away from the patterns, it increases. The shaded area is an error area. Any patterns in the shaded area will give one classification for the Euclidean, but a different one from the city block. So don't worry about that too much, because if the clusters are well defined, if I have a couple of clusters there, those are all the patterns which are black, and these are all the patterns which are red. It would separate all these patterns correctly, all the millions of patterns that are in there, and it would get all the millions of patterns in there correctly. So it would still work. It's only when we get patterns which are dissimilar and moving away from these clusters, if we had a pattern in this region here, the blue pattern, if I'm using the city block, is belonging to this class, but if I'm using the Euclidean distance, the blue pattern belongs to the red class. Is that perfectly clear? You understand how the error arises? Okay, moving on, and this is still revision. There is going to be times with the approximate distance where all the intersections are going to be linear distances. If I arrange for the city block this problem, and it's usually when the axis is 45 degrees, I will have a square there. I should have done that in red, never mind. I will have a square there. I will have another contour there. I can align them up so that we have a contour that is there, and that's overlapping. So this is 1, this is 2, this is 1, oh, this is 2, this is 1. And if I draw a third one in there, it's going to come somewhere like that. It's going to come up there. It's going to go across there. I won't draw it all because it'll get confusing. And if I put a black one in there, it's going to come down here. It's going to go across there. It's going to come across out there. It's going to go up there. And what we have, if you draw this very carefully, is we have an intersection of lines. This will be the intersection of the two contours, comes down there. When we get to the three contours, we've got that intersection there. And we've also, if I've drawn it in properly, that carries on up there, we've got an intersection there. There's no point intersections on the squares because they're exactly lined up. It happens when the angle between the points is 45 degrees. It could happen in real life. It could happen in dimension. And what we now have is a decision surface, which is along there. We've got all the values between 2 and 3 will be an overlap. And we get, in the case of 2 dimensions, an area coming out. So if I remove the contours, the decision surface and shade this in because it's an area. The decision surface, a line there, becomes an area. And there we've got the decision surface there. Anywhere in the shaded area, so that particular alignment of patterns is equidistant from the red and the black. So a pattern there, equidistant. Even though the Euclidean distance is different, the city block distance will be the same. And when you're using this, you can tell that something's gone wrong or this effect has occurred because you will get lots of patterns which are equidistant from reference patterns. And that is usually unlikely to happen. So if you have a situation like that, then we've likely got this volume opening up. And of course, there's an instability because if I move this pattern slightly, the decision surface starts off as the limit of that area. The center is the same and down there. If I move it up there, down there, this takes over. So we have in one case a decision surface that looks like that, and we move it up, the decision surface now looks like that. And so if we were repeating the data and we had slightly different noise, bit of noise on the reference patterns, one could find that in this case the red surface was taking place, the black surface was taking place, and a pattern in there would give ambiguous classification. So it's a little danger in using that approximation. And that's pretty well where we were at the end of the last lecture, and I hope you understand that. Right, I'll give you another approximate distance, and I want to go through this fairly quickly. And this is the square distance. And the equation of the square distance is ds is equal to the maximum. We're using a maximum operator on the dimensionality, I equals 1 to d. And again, we're using the mod of the difference between elements. And again, the order doesn't matter. And if we now plot a contour of equidistance using that approximate distance, let's take a point 2,2. Right, x equals the vector 2, 2. Somebody give me a distance using that, which is 1 from 2, 2. 1, 2, great. So 1, 2. 1, 2. There we are. There's a point there. Just another one. 2, 1. 2, 1. There we are.
1.5, 1.5.
What? Thank you. We've made a shortcut. 1.5, 1.5. Had you have done the 3, 2 and the 3 1s, we've got 4 points, and you might have said, hey, it's a circle. But there's a genius there who's told me 1.5, 1.5 is a vector, which is a square distance of 1 from 2. Why? 2 minus 1.5 is 0.5. Ah, you're wrong. You're wrong. That's only 0.5, because it's a maximum operator. Try again. I thought you were bright. No, you're just ordinary. Try again. Another pattern. Let's put in the 3 1s. The 3 2 and the 1 2. We've got the 1 2 there, and we've got 2 1, which is there, and
That's 1, 1.
that's 1 1. Sorry, 2 1. 2 1 we've got there. Yes. One more.
2, 3.
2 3. 2 3 is there. Right, now give me another one. 1 1. 1 1. Good. First element distance 1. Second element distance 1. The maximum, of course, is 1 because they're both 1. 1 1. And 1 1 is there. Now, it's not going to be a circle around those first 4, and I haven't drawn this very accurately. What do you think the shape of the contour is? There's a clue in the name. It's a square. So if you've drawn that accurately and do that in your own time, that becomes the square contour of equidistance, which is geometrically the same as the city block, but rotated in 2 dimensions by 45 degrees. So we're going to have exactly the same problems. I won't go into it, you can do it yourself. You're going to get dog leg when they overlap, you're going to get voids opening out, and it's going to behave in exactly the same way as the city block distance. But the voids, the hypervoids, the instabilities are going to occur in different positions in that pattern space compared with the city block. So you have the option that the city block, if it's giving you lots of rejects, got problems with the surface opening out, forget about the city block, use the square distance, because it will have the same problems, but it will be in a different area. So if the city block doesn't work, the square will. If the square doesn't work, the city block will. So that's all I really want to say about the square distance. Right. Last year there was an exam question on distance classifiers. So, would you like me to give you a typical example? No, you're not done really, it's all simple, isn't it? Won't bother with examples? You might as well do. You're not enthusiastic. Do you want me to do the example or not?
Yes.
Yes.
Right. Let's see if I can find one that works. Yeah. A predictor for good customers for an insurance company. Something I think I went through a few weeks ago when I was changing my insurance. Because one bloody company was charging me £650 a year, and another company, which was even more reputable than the first one, was charging me £180 a year. The perfect customer for an insurance company, 5 questions, there's most probably 50 in real life. These are questions which you can grade from 0 to 10, like how many driving offences have you had, 0, 10 or more, or something in between. What's the capacity of your car, 10 cc's to 50 megalitres or whatever. And so they are graduated measurements of properties. And for a good customer, we find that this is going to be 5 dimensions. Is it coming in on the board? Oh yes, just about. We find the good customer, the typical customer like me, has a vector 5, 3, 6, 9, and 2. There is the vector. 5-dimensional space, we can't draw it. We've got to rely on the maths. And do you drive? Who drives here? Oh, yes, a reckless guy there, I can see him. Yes, his number is B, and this is good, accept. And this would be reject, if you want to put meanings on the classification. And B turns out to be the vector 9, 8, 2, 4, and 7. And I come along. No, that's me. That was a good one. You come along, assuming you're a driver, and you do the questionnaire, and you submit your pattern X, and you happen to be, well, give me some numbers between 0 and 10.
8,
8,
1,
1,
3,
3,
5,
5,
2.
2. And this is a potential customer. Right. Use the Euclidean distance to determine whether I accept or reject X. Now, to save time, the first 3 rows, work out the Euclidean distance. No, let's even do it more. The first 2 rows, this row and this row, work out the Euclidean distance AX. Right. These 2 rows, work out the distance B, Euclidean distance BX. Right. It gets easier to come back here. This row, work out the city block distance AX. This row, work out the city block distance px. This row, work out the square distance ax. And you three guys, the square distance bx. And you've got 2 minutes to do it in.
I think it's just checking it out.
And when somebody has an answer, shout out and I'll put it on the board and then we'll see if we agree. With the Euclidean, I'll accept the square, don't bother with the final square root, it doesn't matter. It's the last operation you do, so, okay, what's the square distance? Anybody completely lost? Good. And you find anybody finding this trivially simple? That's an exam question. It would be 25% of a pass on the paper if you had the format we used last year. Isn't it simple? No wonder you're all going to get firsts. Oh, I've got to do one on board. AX Euclidean distance. It's going to be 5 minus 9, which is 4 squared, which is 16, plus 5 squared is 25, 16 and 25 is 41, plus 6 minus 2 is 4 squared, 41 and 16 is 57, and then 9, 63, and another 25, 63, 88. I think that is root 88.
You did A and B.
Did I?
5.
That's a method.
Gotcha.
I'm here in root 30. Root 38, AX. Okay. The rest of you see if you agree with him. Let's have BX.
91.
91, root 91. So that would classify as X belongs to A. Shorter distance, shorter square distance. Now the city blocks, please. That's easier. The rest of you who've done the Euclidean distance, try the square distance, because there's not many people at the back doing the square distance.
I got 12, this is 1 minute.
12 AX.
Yeah.
12 BX city block. 11. Interesting. And the squares. When I say the squares, it doesn't involve the square operation arithmetically. The square is the shape of the contour in 2 dimensions. It's a cube in 3 dimensions, it's a hypercube in 2 dimensions. Oh, let me do a square one on board. AX. The first difference is 3. The second difference is 2. 3 is the biggest. The third distance is 3. 3 is the biggest. The fourth distance is 4. 4 is now the biggest. The fifth distance is 0. I think the square distance is 4. Now BX. 1, 7, 1, 1, 5, 7. Now that is interesting because we're getting A, X belongs to class A for Euclidean, but we're getting X belongs to class B for city block.
You mean for square?
Are these correct? Do you all agree with those?
Can you calculate the city block and show how to do it?
You want me to calculate this one or this one?
The BX, yeah.
BX, right, for the city block, BX. Right, it's the sum of the mods, and the mod for the first element is 1, second is 7, gives me 8, the third is 1, gives me 9, the fourth is 1, gives me 10, and the fifth is 5, gives me 15. I reckon that's 15.
Yeah.
Right, now that ties up. They're all giving the same classification. It's shorter, it's closer using Euclidean. It is closer using city block. And X belongs to A there. And that's how you use it. So if you want to match people on their Facebook likes, you just create a vector. Same format for everybody, and you can start doing manipulative things and sending messages and contacting people according to their supposed similarities and properties. And that's using the distance classifier. Right. It doesn't always work. I'm always interested in when things don't work, because that's a challenge. Let's go to binary patterns. Let's take a typical vertical bar. There it is. That wouldn't be a picture for the distance classifier. It would be a 9-element vector. Starting scanning from the origin, let's assume white is 0 and cross is 1. That pattern, let's call it X, equals 0, 1, 0, 0, 1, 0, 0, 1, 0. So there is my 9-element vector. Now, if I put in a test pattern, and I put in that one, you as a human, you're looking for a vertical black bar. Is that a vertical black bar?
Yes.
Yeah. That's my hand up. That's my hand up. Right, what is the Euclidean distance between that pattern and let's call this, what should we call it, K. Now remember binary, there's a shortcut to take. Don't go through the Euclidean arithmetic. The difference of elements, if A and B are binary, is the same as the mod of the elements. which is the same as the XOR operation. And the XOR operation, if you sum it over each comparative pixel, is simply saying, are they the same, 1, 1, 0, 0, or are they different? So the different ones will accumulate the distance. So looking at those two pictures, what's the distance between them?
6.
6. Everybody see that? Got that? Right. xi minus ki squared. That's the operation you're doing Euclidean. That, because x and k are 0 or 1, they're binary, is equal to the mod of xi minus ki. And that, if you want to implement it in logic, is exactly the same as xi exclusive or ki. And in English, exclusive or, oh dear, we're back to level 1 now. X and k, and this is f if you like, 0, 0, 0, 1, 1, 0, 1, 1, and the XOR is going to be 0, 1, 1, 0. Remember, I'll take you out for a nice meal tonight. I'll pick you up outside the university. 6 o'clock sharp, I'll be driving my Bentley or my Ferrari. Exclusive or. And that's just the difference. So, the same, different 1, different 2, same, different 3, different 4, same, different 5, different 6. The distance between x and k is equal to 6. Yes? All agree with that? Right, now use your perception and classify this pattern. Is that a vertical bar? Well, unless you're a physicist, I think you would say it's not a vertical bar. The physicists will see details, you know, they know everything about nothing, so they'd say something about that. That is not a vertical bar by human perception. But what is the distance between nothing and x? 3. So we've got a dilemma. The distance there is 3, and the distance there is 6. So there's a case where the distance classifier could screw up. And look to biology for solutions. Clearly, there's something to do with positioning here. And if I want to study the details of your superb appearance, I don't come in looking at him. I can just see you as a blur there. What do? Gotcha. And we concentrate the image in humans on the center of the eye, and we even have the neck to move around to see who you are. So the solution to this is image processing. Which will come along next term. But of course, image processing, what would you do? You could do with a run code, remove the leading zeros. If we transform this pattern to that by shifting left, I'm putting noughts in there, it should be blank, shouldn't it? I transform that to that, and I do the same with that. Of course, the patterns then become exactly the same, and bang, you've got it. So that's one of the problems that you have to be aware of with the distance classifier. The other thing, of course, is the vector that you're calculating has to be normalized. It has to be within a fixed range. If you allow zoom, the same image closer up can have bigger element values. If I had a coding of a pattern, which was x equals 2, 2, and I increased the zoom, the size of it, that could be a polar vector shape with sample angles of 180 degrees, just the maximum and the opposite radius. If I were to zoom that image out, that could become 5, 5. Exactly the same image, but of course in your pattern space, it's moved it, wow, completely out. So you've got to make sure that there is a fixed format for the elements, and they go between a minimum and a maximum value. And the maximum value you use is 10 or more. Go back to the driving example, 0 to 10 driving offences, and you've got 20. 10 plus would be 10. Okay. Right. Another little trick. How do you sabotage a company that is using a distance classifier to do predictions from its marketing? Let's take a two-dimensional case so we can see what's going on. Let's have a cluster here, and let's have a cluster here. Right. If I was using those three patterns, it would be a sort of piecewise linear surface. You could work it out between them from the nearest of the reds and the nearest of the blues midpoint. But supposing I hacked into your system and I deliberately, or it could happen by mistake, I happen to put a red pattern in that class. Now what that's going to do, it's going to take a huge hole out of this class, because all the patterns in this region are going to be closer to the red than the blue. And we will get that information coming out, because we are relying on the single closest nearest neighbour to make the decision. Any solutions for that problem? We're only using one distance, yes?
To look at all the patterns.
Look at more distances, and this leads to a simple modification called the kth nearest neighbour. Which means instead of finding the closest known reference pattern, you've got the list of all the distances when you're operating the classifier. Don't make the decision on the closest. Find the k closest patterns, where k is greater than 1. The closest 5 patterns. And what would happen in this case, if I had a pattern in there, I've got a green pen, if I had a test pattern in there, clearly it's closest to the faulty or the sabotage red pattern. But if I take the next closest one, it's going to be blue, it's going to be blue, it's going to be blue. So I have 4 distances. 3 of them are saying it's blue. 1 of them is saying it's red. And that will smooth out the surface, and it will protect it from either erroneous patterns in the reference set or somebody trying to hack it. So the kth nearest neighbour is you make the decision on the k. Use k nearest distances. A bit more processing, but not too much, and that will give the method more resilience. And of course, that's only in 2 dimensions. In 10, 100, 1,000 dimensions, the same applies. Okay, so that really would be the standard way, the safest way to implement a nearest neighbour classifier, even if you're using approximate distances. Gosh, we've got to the end of the lecture, and I wanted to start on neural networks. Right, let's just give you a taster. The next part of the course is it showing up there? Here, just about. Right. Why use neural networks? What's all this nonsense about neural networks?
Classify how to do regression.
Right, yes, sort of, but more fundamentally, you're talking to your father or your mother who doesn't know much about computing. What's the point of neural networks? It's a processing structure that can solve some fantastic problems. The human brain is a data processor. The human brain, it's electrical signals. Everything you do as a human, it's an electrical process in the brain. Yes, everything. Which means for potential products, you can plug into the nervous system, and if you send the right signals in the nerves, you will get any sensation in the brain possible. Yeah, interesting concept. The next important thing is the human brain doesn't need programming. There's no C++ up there or whatever. There's no Java. And we're pretty good at it. So that's an interesting fact. The human brain also is quite slow compared to computers. We'd like to know how it works. Can I give you a quick example? Anybody got a banknote on them? I know they're old-fashioned. You got a banknote, somebody? No, all cash-free, is it? Oh, look, there's the old-fashioned metal Greek cards. I'll smooth it out. 20 quid, thank you very much. Come out here, my friend. Usual old trick, you've seen this many times before. Now there is a brain. Put your fingers up. Come on, smooth one, have you? Right, put your hands up like that. And the idea is for you to catch it, right? You ready? Right, come on, I haven't finished with you yet. Right, let's give you a better chance. You've got loads of banknotes. I'll give you a real chance now. Oh, come on! Right, give you a real chance. Oh, that's too hard. You should have caught that. Right. Now let's give his brain a little bit more work. Right. What's your girlfriend's name? It should have worked better than that. But the brain is pretty slow. So we're not looking at it. Oh yes, give it back to him. Yeah. Or me. So we're not looking at a processor that's ultra fast. And in fact, the speed of transmission, because it's not actually electrons in the human body, it's ions, sodium and chlorine ions, and one or two other things. So they're bigger, and they have to diffuse through membranes. So the signals in the human brain, they only go at about 10 meters a second, as opposed to the speed of light. So that's interesting. It's a slow process. But what it is totally parallel. And what you'll have in the brain is, if you're a good electronic engineer, about 10 to the 11 cells. In English, that is about 100 billion. Rumours have it that mechanical engineers have less. And each cell has an input. The number of inputs could be 5,000. So what you've got up there is one of the most connected systems in the world. Put some numbers against it. It is unbelievable. And of course, the other thing is, all our brains are different. There's nobody exactly the same. So we would love to know how that brain works. And we've got two options. And one is the option taken by neuroscientists. And they will take you and they will put you in a scanner. Scanner is an electrical machine which was devised by people at EMI 20 years ago, 30 years ago. They hadn't got the commercial sense to develop it, so it went off to Siemens. Grudge I have. They'll put you in a scanner and they'll try and stimulate you. They'll play soft music and see where the brain activity is taking place. They'll make it cold and another part of the brain gets active. What else might they do? They might frighten you. That bit works. And they can discover about 60 regions of the brain. And they start to say, hey, we're getting an understanding of this piece. No, they're not. It's like taking your phone, It's like taking a phone. I want to reverse engineer this. I'm a Korean company wants to do a fake. So I put my hand on there. I make a phone call there, and that part of the phone gets hot. Well, that's the telephone bit. I send a text message. That's not that. Do Google searches over there, and you can identify regions of activity with various functions. But it doesn't give you a clue what the electronics is. So we, as engineers, take a different approach. And we start off with a single brain cell, which has inputs and an output, and we try and get a model of that cell. Now, it doesn't have to be biologically correct, it has to be interesting. And so the first thing we're going to do next week is look at a model of a single neuron. It's a very simple approach. We're starting with the simplest possible, but I want to give you understanding as to how it works. Because with neural networks, 99.9% of the population haven't got a clue as to what they do, and how they work, and what their limitations are. So I want to try and make you inspired engineers who know a little bit about what the model can do, and more importantly, what the model can't do. So that'll come on Thursday. Okay, thanks a lot. Any questions?
Thank you, sir.
Cheers. Cheers.
Thank you.
Thank you. Bye bye, thanks.